A star dies in a cataclysm brighter than a billion suns. From that violent chaos, the universe forges the seeds of all life. This is the cosmos's grandest paradox, where ultimate destruction becomes the ultimate creator. By the end of this journey, you will understand how the very atoms that compose you were born in a stellar explosion. We will trace the journey from a star's final, frantic seconds to the creation of complex matter, uncovering how the iron in your blood and the calcium in your bones were forged in a celestial furnace. How does a chaotic supernova explosion produce the precise ingredients for planets and life itself? What does it mean to know that we are all made from the ashes of long-dead stars? A star is a cosmic factory, running a continuous production line deep within its core. For millions of years, it performs this relentless work, beginning as an unassuming, cold cloud of gas and dust drifting through the emptiness of space. The story starts when gravity, the universe's great architect, decides to pull this scattered material together. The cloud collapses, spinning and heating up until the pressure and temperature at its heart become so unimaginably intense that atoms of hydrogen are forced to merge. This is the moment of ignition, the birth of a star, as it begins fusing hydrogen into helium and pouring light into the void. This fusion process is the star's engine, a powerful reaction that pushes outward, perfectly balancing the inward crush of its own immense gravity. For most of its life, this stalemate holds, but a massive star is a glutton, consuming its hydrogen fuel at a ferocious rate. When the hydrogen in the core finally runs out, the balance shatters. Gravity wins this round, compressing the core further until it becomes hot and dense enough to ignite the next fuel, fusing helium into carbon. The star adapts, creating a layered structure like a cosmic onion. A shell of hydrogen fusion now surrounds a core of helium fusion. This cycle of fuel exhaustion and gravitational collapse continues, each round creating heavier elements. The helium core eventually fuses into carbon and oxygen. In the most massive stars, this process continues, forging neon, magnesium, and silicon in successive shells, all building toward a final, pivotal element. Each new layer of fusion provides a temporary reprieve, but it is a race the star is destined to lose. The entire structure, with its concentric shells of increasingly heavy elements, is a meticulously assembled setup for a single, world-shattering event. This long and stable life is merely the prelude to the drama of its death, where the true alchemy of creation will finally be unleashed. Deep within its layered heart, the star finally creates an element that spells its own doom. Iron. This is not like the other elements forged in the stellar furnace. Iron is a dead end. To fuse iron into something heavier requires energy. It does not release it. It is the ultimate cosmic parasite, draining the star's last reserves of power. So when the iron core grows large enough, the star's magnificent engine simply stalls. It is as if a colossal power plant has burned through its very last lump of coal. The relentless outward pressure from fusion, which held gravity at bay for millions of years, vanishes in an instant. And gravity, patient and unforgiving, seizes its moment. The star's own immense weight, no longer supported, now comes crashing inward. This is the point of no return. The stable, ordered structure of the star, with its neat concentric shells, shatters into pure, unfettered chaos. In less than a single second, a core that was once larger than our entire Earth is compressed into a sphere just a few dozen miles across. The collapse is so violent, so swift, that it triggers a rebound of unimaginable force. setting the stage for the star's final, spectacular act of creation. The star's core is now a runaway collapse, plummeting inward at speeds approaching a quarter of the speed of light. In a fraction of a second, a core that once rivaled our entire planet in size is crushed into an unthinkably dense ball of matter just a few dozen kilometers wide. The pressure is so immense that it fundamentally rewrites the structure of matter itself. Protons and electrons, the basic building blocks of atoms, are forced to merge, transforming into neutrons and releasing a ghostly flood of particles called neutrinos. This is the birth of a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. But this violent compression is not the end, it is merely the trigger. The formation of the neutron star halts the inward free fall, and the core stiffens into an almost impossibly hard surface. The collapsing outer layers of the star, still rushing inward at a significant fraction of light speed, slam into this newly formed, immovable wall. The energy of this impact is beyond comprehension, creating a shockwave that rebounds outward with the force of a quintillion nuclear explosions. This is the moment the supernova explosion begins, a chaotic firestorm that will blast the star's guts across light years of space. It is from this unbelievable violence that the universe will begin its most delicate work, forging new order from the ashes of the old. This rebounding shockwave now faces its greatest challenge, a waterfall of star stuff still pouring inward. For a brief, critical moment, the outward blast stalls, caught in the overwhelming gravitational pull of the collapsing star. It seems the explosion might fail, that the star will simply crush itself into silence. But the universe has another, more subtle force waiting in the wings. The newborn neutron star at the heart of this chaos is searingly hot, 1 trillion degrees Celsius, and it is screaming. Its cry is not made of sound but of neutrinos. These ghostly particles born from the core's collapse now pour out in an almost unimaginable flood. We are talking about a number so vast it defies human intuition. In that single second, the supernova releases more neutrinos than the total number of photons emitted by every star in every galaxy in the observable universe. This immense neutrino wind catches the stalled shockwave from behind, injecting it with a colossal surge of energy. It is like a cosmic defibrillator, delivering a massive jolt to a dying heart. The shockwave revives, energized beyond belief, and begins its final, triumphant march outward. It rips through the star's remaining layers, tearing them apart from the inside out. This is the true beginning of the supernova explosion. The star's own guts, enriched with a lifetime of nuclear fusion, are now violently blasted into the void. In that chaotic expulsion, the raw elements forged over millions of years are set free, ready to become the building blocks for everything that will ever follow. These ghostly neutrinos carry away a staggering 99% of the star's entire gravitational energy, yet for all their power, they are the most elusive of particles. A neutrino can pass through a light year of lead without slowing down. So how can something that barely interacts with anything become a key architect of cosmic destruction and creation? The answer lies in the unimaginable density of the collapsing core. Here, matter is packed so tightly that even these phantoms get a chance to make their mark. As the torrent of neutrinos streams outward from the newborn neutron star, they slam into the incredibly dense inner layers of the star. The sheer number of collisions is so immense that the neutrinos deposit a fraction of their colossal energy into this falling material. It is this final, critical push that helps the revived shockwave finally tear the star apart. But their role does not end with the explosion itself. As the neutrinos flood through the expanding cloud of stellar debris, they perform a second, more subtle act of alchemy. They transform the very elements they help to create. A neutrino can strike a nucleus and flip a proton into a neutron, or a neutron into a proton. This process, called Neutrino Nucleosynthesis, forges a unique set of rare, heavy elements. Elements like fluorine, which strengthens our tooth enamel, and the radioactive aluminum that still heats the interiors of young planets, are thought to be forged directly by this ghostly neutrino rain. Their escape into the cosmos is the final, crucial step. By carrying away that immense energy, they allow the explosion to complete its work, seeding the surrounding space with a newly forged, complex blend of elements. The chaotic fireball becomes a carefully curated dispersion of cosmic ingredients. Within the supernova's expanding fury, a frantic and miraculous production line roars to life. As the shockwave rips through the star's outer layers, it creates a cauldron of unimaginable heat and pressure. Here, atomic nuclei are bombarded by a blizzard of free neutrons. In these extreme conditions, a remarkable process unfolds, one of the universe's most crucial acts of creation. It is called the rapid neutron capture process, or the Are process for short. In normal stellar fusion, nuclei build up slowly, adding one proton at a time. But here, in the chaotic heart of the explosion, there is no time for such delicate work. The flood of neutrons is so intense that atomic nuclei cannot withstand it. They gobble up dozens of neutrons in just a few seconds, a frantic feast that transforms them into extremely heavy, unstable versions of themselves. These overstuffed nuclei then undergo a dramatic transformation, with some of their newly acquired neutrons decaying into protons. This single, rapid sequence forges many of the heaviest elements in the cosmos in an astonishingly short burst. The gold in a wedding ring, the silver in a piece of jewelry, even the uranium that powers nuclear reactors, all were likely born in this violent, seconds-long event. Think about that for a moment. The entire inventory of these precious and powerful heavy elements, everything heavier than iron, was minted in the frantic final breaths of dying stars. The chaotic fireball becomes a cosmic mint, stamping out the final, crucial entries on the periodic table and completing the set of raw ingredients the universe needs to build complex worlds. The supernova's fury does not last forever. As the colossal fireball of enriched gas continues its journey outward, it inevitably begins to cool. This expanding cloud, a chaotic mixture of every element from carbon to gold, now enters its most delicate phase of construction. In the relative quiet after the explosion, individual atoms and simple molecules start to bump into one another within the nebular haze. In the frigid vacuum of space, these collisions are not violent. They are gentle encounters where particles simply stick together. It is a slow, patient accumulation, like a fine mist freezing into intricate snowflakes. Silicon atoms link with oxygen to form silicates, the very stuff of sand and rock. Carbon atoms bond into chains, creating the foundations for soot and graphite. Layer by layer, microscopic motes of dust begin to coalesce. These are not the simple atoms forged in the star's heart, but complex, solid particles. This is the universe performing its most fundamental magic trick, transforming a diffuse and disordered cloud of gas into trillions upon trillions of tiny, structured seeds. Each minuscule grain, no larger than a speck of smoke, carries within it the legacy of the stellar explosion. They are the primordial bricks, the essential construction material without which planets like our own could never form. The chaotic death of a star has given birth to the fundamental seeds of new worlds. These microscopic dust grains now drift within a vast, glowing cloud known as a supernova remnant. The most famous of these is the Crab Nebula, a beautiful, tangled web of glowing filaments that we can still see expanding today, nearly 1,000 years after the original star exploded. This remnant is far more than a cosmic gravestone. It is a dynamic and violent nursery. The initial explosion launched a shell of debris at millions of kilometers per hour, and this expanding fireball continues to plow into the surrounding interstellar medium, the thin gas and dust that fills the space between stars. This is not a gentle process, it is a cosmic bulldozer, sweeping up and compressing the ambient material of the galaxy into dense, massive walls. At the heart of the Crab Nebula, the collapsed core of the dead star spins furiously, a pulsar that bathes the entire cloud in a relentless wind of energetic particles, keeping it hot and agitated. It is within these compressed, turbulent walls that gravity finds its next opportunity. A passing ripple of density, the shockwave from the remnant itself, can be the final nudge that pushes a precarious cloud of gas over the edge. The cloud collapses under its own weight, and deep within its new core, the pressure and temperature rise until hydrogen atoms are forced together. A new star ignites, its light piercing the cosmic gloom. In this profound cycle, the violent death of one massive star does not just spread the ingredients for life, it actively builds the factories where those ingredients will be used. The supernova remnant becomes a cosmic trigger, ensuring that the legacy of destruction is a new beginning. But the universe, it seems, always keeps a wild card up its sleeve. Supernovae are not the only cosmic forges responsible for the heaviest elements. There exists a second, even more violent and spectacular pathway to creation. When two neutron stars, the incredibly dense remnants of supernova, are locked in a fatal gravitational dance, they spiral inward over millions of years until they finally collide. The energy released in such a merger is staggering, outshining entire galaxies for a brief, brilliant moment. This collision creates conditions far more extreme than even a supernova can muster, generating a furnace of unbelievable density and a torrent of free neutrons. It is within this maelstrom that the rapid neutron capture process, the Are process, finds its ultimate expression. Here, atomic nuclei are bombarded so ferociously that they can capture neutrons at a rate far beyond what is possible in a single dying star. These mergers are thought to be the primary cosmic source for the very heaviest elements, including most of the gold and platinum in the universe. Picture the gold in a necklace or a computer component. There is a very good chance its atoms were not forged in a supernova, but in the spectacular head-on collision of two dead stars. This reveals a profound duality in the cosmos's creative power. Order emerges not just from the chaotic death of a single star, but also from the violent, choreographed union of two stellar corpses, spraying the void with an even richer cocktail of elements essential for building complex worlds and ultimately life itself. These microscopic dust grains, enriched with the legacy of stellar death, now find their ultimate purpose. They drift into a new, swirling cloud of gas and dust that is collapsing to form a new star. As this young star ignites at the center, its light and heat push the lighter gases like hydrogen and helium outward, leaving behind a vast, flat, rotating disk of material in the inner system. This is the protoplanetary disk, a cosmic construction site where planets are born, and it is absolutely peppered with our supernova-forged dust. The chaotic elements from that ancient explosion have found a new, structured home. Within this disk, the gentle dance of accretion begins. Those microscopic dust grains, each a speck of carbon, silicate, or metal, start to stick together. Electrostatic forces make them cling to one another, like a fine, magnetic dust assembling itself into fluffy, fractal snowflakes. These tiny clumps grow into larger pebbles, then into boulders several kilometers across, known as planetesimals. This is no longer a gentle dance, but a gravitational game of bumper cars. The largest of these planetesimals begin to exert a significant pull, sweeping up more and more material through countless collisions. Over millions of years, they grow from rocky embryos into full-fledged planets. The inner part of the disk, hot from the young sun, favors the condensation of metals and rocky silicates, giving rise to the terrestrial worlds like Earth. Farther out, where it is cold enough for ices to form, the cores of gas giants rapidly accumulate vast atmospheres of hydrogen and helium. Our entire solar system, with its stunning diversity of planets, is a direct product of this process. Every mountain, every ocean, every breath of air is composed of material that was once fused in the heart of a massive star and then blasted into the galaxy by its supernova death. We are not just living in the universe, we are the organized, conscious remnant of its most violent and creative acts. This final act of cosmic delivery is how the universe literally seeds life across the galaxy. The supernova has forged the critical elements, but it is a second wave of cosmic messengers that brings them to barren worlds. Asteroids and comets become the galactic supply ships. These rocky and icy bodies, formed from the same dusty debris cloud that birthed our solar system, are packed with the supernova's legacy. For hundreds of millions of years, the early Earth was subjected to a ferocious bombardment, a celestial hailstorm of these objects. Each impact was a delivery carrying precious cargo from the stars. They brought water, the universal solvent, in the form of ice locked within comets and asteroids. They delivered carbon, the backbone of every organic molecule. They rained down nitrogen, essential for building proteins and DNA. They even supplied phosphorus, a crucial component of our cellular energy currency, and sulfur, vital for many biological processes. Without this violent rain of material, our young planet would have been a dry, desolate rock, devoid of the very ingredients needed to spark life. The chaos of the supernova explosion was channeled into the orderly orbits of comets and asteroids, which then acted as precise delivery vehicles, targeting nascent worlds with the building blocks of biology. Every living thing on Earth is a testament to this ancient interstellar supply chain. The iron in your blood that carries oxygen, the calcium in your bones that gives you structure, the very DNA that codes your existence, all of it was assembled from atoms forged in a star that died long before our sun was even born. We are not just stardust in a poetic sense, we are the organized, conscious result of stellar alchemy, a living legacy written in the language of elements born from cosmic chaos. This grand cycle of cosmic recycling began with a universe of almost perfect simplicity. In the aftermath of the Big Bang, the cosmos contained only the lightest of elements, a pristine fog of hydrogen and helium. This was the universe's raw, primordial material. From this simple gas, gravity sculpted the very first stars, colossal behemoths that lived fast and died young in titanic supernova explosions. Their deaths were the universe's first act of complex creation, polluting the void with newly forged carbon, oxygen, and iron. This enriched gas did not simply dissipate. It was gathered up again by gravity, mixing with the remaining primordial hydrogen to form a second generation of stars. These new stars were different from their ancestors. They were born with a richer chemical inheritance, a dash of stardust within them. This small addition of heavy elements made a profound difference. It allowed for the formation of solid dust grains around these new stars, the essential seeds for planets. With planets came the possibility of rocky worlds, of oceans, and ultimately of life. Each stellar generation enriches the cosmic pool. The gas between the stars, the interstellar medium, becomes steadily more metallic, a term astronomers use for any element heavier than helium. This increasing metallicity is the universe's way of bootstrapping itself toward complexity. A third generation of stars forms from gas that is even richer, making rocky planets more common and more diverse. Our own Sun is a product of this long chain of stellar lives and deaths. It is a third-generation star, its substance containing the ashes of countless supernovae that exploded billions of years before it was born. We are living in a universe that is actively building itself, one stellar explosion at a time. The iron in your blood and the silicon in the ground beneath your feet are not just stardust, they are the recycled legacy of generations of massive stars, a testament to a cosmos that is forever transforming its own chaos into intricate, beautiful order. This single star's death sends ripples across its entire cosmic neighborhood, reshaping the galaxy itself. The colossal energy of a supernova explosion does far more than simply forge new elements. It carves the landscape of star formation for eons to come. Picture a galaxy as a delicate ecosystem, a vast rotating disk of gas and dust where stars are born in cold, dense clouds. When a massive star explodes, it acts like a sudden forest fire in this celestial wilderness. The blast wave and intense radiation heat the surrounding interstellar gas to millions of degrees, preventing it from cooling down and collapsing into new stars. In these vast supernova-cleared bubbles, star formation is effectively shut down. The galaxy's stellar nursery is temporarily closed for business. Yet, at the very edges of these expanding bubbles, something else is happening. The shockwave from the explosion slams into neighboring, colder clouds of gas. It compresses them, squeezing the material just enough to push it over the critical threshold where gravity can take over. This triggers a new, cascading wave of star birth. It is a cosmic paradox where one star's violent death simultaneously stifles creation in one place and kindles it in another, orchestrating the rhythm of galactic life. But the influence of supernova reaches even further. When many of these explosions occur in rapid succession, their combined energy can create a galactic wind, a powerful outflow that blasts vast quantities of gas completely out of the galaxy. This process is vital for regulating a galaxy's growth. By ejecting this raw material, supernova prevent the galaxy from forming new stars too quickly, effectively putting a brake on its own development. Without this self-regulating mechanism, a galaxy would burn through its fuel supply in a short, furious burst, leaving behind a stagnant system devoid of the long-term evolution needed for planetary systems like our own to emerge. These stellar explosions are not just local events, they are the primary architects of a galaxy's structure, its chemical richness, and its very destiny. They are the force that transforms a simple cloud of primordial gas into a complex, evolving island of stars, planets, and potential life. Even amidst the stellar cataclysm, a hidden clockwork is ticking. The brilliant flash of the supernova does not simply fade into darkness. It follows a precise and predictable dimming pattern known as its light curve. This is not random chaos, but a radioactive countdown baked into the very heart of the explosion. The initial, staggering peak in brightness is fueled by the sudden release of the shockwave's energy. But what powers the long, slow fade that can last for months is something far more specific. Deep within the expanding cloud of debris, the explosion has forged a significant amount of a radioactive isotope called nickel-56. This unstable element is the supernova's hidden battery. It immediately begins to decay, transforming into cobalt-56 with a half-life of about 6 days. This rapid decay releases a flood of gamma rays that heat the expanding debris, keeping the supernova shining brilliantly. Then, the cobalt-56 takes over. itself decaying into stable iron-56 with a half-life of 77 days. Each step in this chain releases energy, and the predictable nature of radioactive decay imposes a strict timetable on the fading light. It is this reliable sequence that allows astronomers to use certain types of supernova as cosmic mile markers. Because the physics of nickel and cobalt decay is universal, the true peak brightness of these supernovae is always the same. By measuring how bright or dim the explosion appears from Earth and comparing it to the known intrinsic brightness revealed by the light curve's shape, scientists can calculate precise distances across the universe. This radioactive heartbeat, born from the explosion's chaos, provides one of the most fundamental rulers for mapping the cosmos. This expanding wreckage becomes a natural laboratory of extreme physics. The chaotic environment of a supernova remnant is a place where nature runs experiments we could never hope to duplicate on Earth. Within its tangled filaments, magnetic fields are whipped into a frenzy, trillions of times stronger than our planet's own magnetic field. These invisible lines of force act like colossal, invisible slingshots. They capture subatomic particles such as protons and electrons and fling them back and forth across the vast expanse of the remnant. With each pass, the particles gain more and more energy, accelerating until they are traveling at a staggering 99.99% of the speed of light. These are cosmic rays, a relentless rain of high-energy particles that constantly bombard our planet from deep space. Every second, hundreds of these particles pass right through your body, silent messengers from the most violent events in the galaxy. Their origin was a mystery for decades, but we now understand that supernova remnants are one of the universe's primary particle accelerators. The turbulent shock waves that mark the outer edge of the expanding blast wave are also perfect sites for discovery. Here, we can observe the fundamental behavior of matter in its fourth state, plasma, a superheated soup of charged particles. The collisions and interactions within these shocks reveal the precise mechanisms of particle acceleration, a fundamental process that shapes the energy balance of the entire galaxy. In this way, the chaos of a stellar death creates the perfect, ordered conditions for us to unravel the universe's deepest secrets. But hidden within this cosmic debris is a radioactive time bomb. Among the many elements forged in the supernova's fury is a particularly unstable one, aluminum-26. This is not the stable aluminum we find in soda cans, but a radioactive isotope with a restless heart. When the star explodes, it scatters this radioactive aluminum across light years of space, where it becomes mixed with the clouds of gas and dust that will one day form new stars and planets. The moment it is created, its internal clock starts ticking. With a half-life of just over 700,000 years, aluminum-26 decays, transforming into a more stable form of magnesium. This process of decay is not silent. It releases a steady, penetrating radiation in the form of gamma rays. Now, picture a young, forming planetary system, a swirling disk of dust and rock surrounding a newborn star. This radioactive aluminum is laced throughout that material, and as it decays, it releases energy. This energy is absorbed by the surrounding dust grains and planetesimals, heating them from the inside out. It is as if each of these early planetary building blocks has its own tiny radioactive furnace buried deep within. This internal heating can fundamentally alter the destiny of a young world. For smaller bodies like asteroids, this heat can be enough to melt their icy components, driving off water and other volatile materials, leaving behind a dry, rocky husk. For larger, forming planets, this radioactive warming can influence the chemical separation of elements deep within their interiors, affecting the very composition of their metal cores and rocky mantles. The chaotic death of a star, therefore, does more than just supply the bricks for new worlds. it also provides the internal warmth that helps to bake and shape them, determining their final structure and chemistry from the very beginning. But this stellar chaos has an invisible architect. Deep within the collapsing star, a hidden force is being wound up to an unimaginable intensity. The original star's magnetic field, once a diffuse and orderly structure, is caught in the gravitational torrent. As the core implodes, it spins faster and faster, like a figure skater pulling in her arms. This rapid rotation twists the magnetic field lines, wrapping them into a tightly coiled knot of energy. The field becomes trillions of times stronger than Earth's, transforming into a cosmic vice grip. This newly forged magnetic monster does not just watch the explosion, it actively guides it. The amplified field can puncture through the star's poles, channeling the outward rushing debris into powerful, focused jets that blast into space at nearly the speed of light. This is why many supernovae are not perfect spheres, but lopsided explosions. The star is literally torn apart along the magnetic seams of its own creation. In the most extreme cases, this process leaves behind a truly bizarre remnant. If the newborn neutron star is spinning rapidly enough, its incredible density and wound-up magnetic field combine to create a magnetar. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's. It is a force so potent that it could wipe the data from every credit card on our planet from halfway across the galaxy. This magnetic fury does not fade quietly. A magnetar can produce starquakes on its crust, releasing titanic bursts of gamma rays and X-rays that ripple through space for thousands of years. Long after the visible light of the supernova has faded to nothing, this invisible, spinning relic continues to shape its surroundings, a permanent and powerful reminder of the ordered forces that once directed a stellar cataclysm. This chaos, it turns out, follows a set of rules. When astronomers train their telescopes on these stellar explosions, they see distinct patterns in the light, a cosmic taxonomy of death. We classify supernovae into two main families, and the key identifier is found in their spectra, the unique chemical fingerprint imprinted in their light. If a supernova's light reveals the presence of hydrogen, it is labeled a Type II. This is the classic core collapse supernova we have been following, the final act of a massive star that still possessed its outer hydrogen envelope when it met its end. But what about stars that have already lost that outer skin? A supernova whose spectrum shows no hydrogen at all, but does show helium, is called a Type 1b. And if it shows neither hydrogen nor helium, it earns the designation Type 1c. These are not different kinds of chaos, they are different chapters in the same story. A Type 1b or C supernova was also a massive star, but one that was stripped bare before it exploded. This can happen in a binary star system, where a greedy companion star gravitationally steals its neighbor's outer layers, or through powerful stellar winds that blow the star's own atmosphere away into space. By the time the core collapses, the star is already naked, its inner layers of helium or even carbon and oxygen exposed to the void. The light curve, the precise way the supernova brightens and fades, provides another layer of order. The shape of this curve tells a detailed story about the radioactive elements forged in the blast, primarily nickel-56, which gives us a direct measure of the explosion's power and the original star's mass. So a Type II supernova with a long, slow decline points to a truly colossal progenitor, while a Type 1c with a brilliant, fast peak might signal the death of a rapidly spinning, highly magnetized star. This entire classification system is our way of reading the biography of a star from its final, violent signature, transforming a flash of indiscriminate light into a structured narrative of mass, composition, and cosmic history. That chaotic collapse often leaves behind a rapidly spinning cosmic cinder. The newborn neutron star, now compressed into a city-sized sphere, possesses an immense magnetic field and a ferocious rotational speed. As this object cools, its magnetic field, which is not aligned with its rotation axis, funnels intense beams of radiation from its magnetic poles. These narrow beams, containing radio waves, X-rays, and more, shoot out into space like the light from a cosmic lighthouse. From our perspective, if one of these beams sweeps across the Earth as the star rotates, we detect a regular, repeating pulse of energy. This is a pulsar, a spinning neutron star that appears to blink on and off with a rhythm so precise it rivals the most accurate atomic clocks we can build. Some pulsars rotate hundreds of times per second, their flashes arriving with a predictability measured in tiny fractions of a second over years and decades. This is the universe's most profound paradox made manifest. From the indescribable chaos of a stellar core's implosion and the violent fury of a supernova, an object of near-perfect temporal order is born. The random, turbulent forces of the collapse somehow impart a clean, stable spin, creating a celestial metronome that ticks for millennia. These pulsars become fundamental tools for navigation, both for our spacecraft and for our understanding of space-time itself. Their predictable pulses have been used to test Einstein's theory of general relativity and to map the invisible gravitational waves that ripple through the cosmos. So the next time you glance at a clock, remember that some of the most reliable timekeepers in existence were born from the most destructive events the universe can produce. This cosmic cycle of destruction and creation is not a distant abstraction. It is written into the very rock beneath our feet. We have found the literal fingerprints of ancient stellar explosions preserved in Earth's geological record. Deep within layers of ocean crust, scientists have discovered traces of a radioactive isotope called iron-60. This is not a substance that forms naturally on our planet. Its presence is a smoking gun, a clear signal that the debris from a nearby supernova once rained down upon Earth. Iron-60 has a half-life of 2.6 million years, which means any primordial supply from Earth's formation would have decayed into nothing long ago. The fact that we can still detect it in specific, datable sediment layers is profound evidence. It tells us that within the last few million years, a dying star close to our solar system sprinkled its freshly forged ashes directly onto our world. This was not a gentle cosmic dusting. It was a direct delivery of material from a stellar corpse. Imagine the sky glowing with a second, temporary sun, visible even in daylight as the light from a relatively nearby supernova reached us. Then, centuries later, a wave of invisible radioactive particles would have begun to filter through our atmosphere, settling onto the land and sea, leaving a permanent, if subtle, mark in the planet's history books. This interstellar contamination had consequences far beyond mere geology. When such a supernova occurs within a few hundred light years of Earth, its effects can be dramatic. The initial flash of light, while spectacular, is likely harmless. The real impact comes later, as a sustained blast of cosmic rays and high-energy radiation from the expanding remnant reaches our planet. This could have stripped away parts of our protective ozone layer for centuries, allowing increased levels of harmful ultraviolet radiation from our own sun to reach the surface. Such an event would have put immense stress on global ecosystems, potentially triggering climate shifts and driving waves of extinction. It is a fascinating and humbling thought that the evolutionary path of life on Earth, the rise and fall of countless species, may have been nudged by the death throes of a massive star light years away. We are not just passive observers of the cosmos, we are participants in its grand and sometimes violent story, with the evidence buried in our own planet's crust. Our own sun, however, will never experience such a dramatic end. It is a cosmic lightweight destined for a far quieter and more solitary fate. When our star exhausts its hydrogen fuel in about 5 billion years, it will swell into a red giant, its outer layers engulfing the inner planets, likely including Earth. But its core will never achieve the crushing densities needed to forge iron. Instead of collapsing into a supernova, it will gently puff its outer layers into space, creating a beautiful but fleeting planetary nebula. What remains will be its exposed core, a white-hot, Earth-sized ember known as a white dwarf. This stellar cinder will be incredibly dense, but it will lack the mass to trigger any further fusion. It will simply cool down over trillions of years, fading from white to yellow to red, and finally to a cold, black lump of carbon and oxygen. This peaceful end reveals a profound cosmic truth. A star like our Sun is a wonderful sustainer of life, but it is not a creator of the fundamental ingredients for new life. It lives a long, stable life and dies a relatively gentle death, but it does not seed the galaxy with the heavy elements necessary for rocky planets and biology. It is the massive stars, the true titans of the cosmos, that bear the unique and violent responsibility of cosmic creation. Their immense mass is the crucial ingredient, the one that generates the unbelievable pressure and heat required to forge elements all the way up to iron and then, in their final, spectacular supernova death, to scatter every element heavier than iron across the galaxy. Without these massive stars and their catastrophic endings, the universe would be a very different place. It would be a cosmos of hydrogen, helium, and not much else, a vast, simple expanse with no planets, no chemistry, and certainly no one to wonder about its origins. On February 23, 1987, a ghostly whisper passed through the Earth, deep underground, inside massive tanks of purified water in Japan and the United States. Sensitive instruments registered a few dozen tiny flashes of light. These were not caused by anything on our planet. They were the faint signatures of 24 neutrinos arriving from a supernova that had just occurred in the Large Magellanic Cloud, a neighboring galaxy. For the first time in human history, we had directly detected the death cry of a star's collapsing core. These neutrinos had begun their journey 168,000 years ago, and they arrived hours before the visible light from the explosion reached our telescopes. This timing was a perfect match for the theoretical models. The initial collapse and formation of the neutron star released the neutrino burst, while the shockwave took longer to rip through the star's outer layers and become visible. That single, fleeting observation transformed our understanding. It was the birth of neutrino astronomy, a new way of seeing the universe that relies not on light, but on these most elusive particles. It confirmed that our basic picture of a supernova's inner engine was correct, turning a chaotic, distant flash into a source of clean, direct data straight from the heart of the inferno. Every supernova since has been a silent invitation, a challenge to build detectors sensitive enough to catch more of these cosmic ghosts and read the detailed story they carry from the moment of creation itself. These brilliant nebulae are more than just cosmic art, they are a complex ballet of force and matter. When we gaze at a Hubble image of a supernova remnant, we are not seeing random chaos, but a portrait of physics painted on an unimaginable scale. Every delicate filament and sweeping arc tells a story of immense power channeled through universal laws. The vast, bubble-like structures are shock fronts, the leading edge of the explosion's energy as it plows into the interstellar medium at millions of kilometers per hour. It is a cosmic bow wave, a permanent record of that first colossal push into the void, and look closer at those intricate, finger-like projections reaching inward. These are Rayleigh-Taylor instabilities in action, a phenomenon you can see in your own kitchen. It is the same principle that occurs when a dense fluid sits on top of a lighter one, and the heavier liquid pushes down in tendrils while the lighter one bubbles up. In the supernova remnant, the dense shell of ejected stellar debris is decelerated as it hits the thinner interstellar gas. The lighter gas pushes through the heavier debris, creating those beautiful, roiling structures. The physics is identical, only the scale is cosmic. Even the delicate filaments themselves are a form of order. They are not solid objects, but tubes of glowing gas, twisted and braided by magnetic fields and turbulent eddies within the expanding cloud. They mark the boundaries where different densities and temperatures of gas collide, causing them to light up like neon signs. The ethereal beauty of a nebula is therefore a direct translation of mathematical and physical principles into visible form. It is the universe's way of making the invisible forces of hydrodynamics and magnetism spectacularly, tangibly real. These violent deaths are far too fast and distant for us to see in detail, so we have built entire stars inside our machines. Supercomputers now allow us to recreate a supernova's final seconds in exquisite, virtual detail. These are not simple animations, they are full-scale mathematical universes, governed by millions of lines of code that encode the fundamental laws of physics. The simulations must account for the crushing force of gravity, the bizarre behavior of nuclear matter, the tangled influence of magnetic fields, and the fluid dynamics of a star tearing itself apart, a field known as magnetohydrodynamics. Every single one of these forces is in a frantic, chaotic dance during the explosion, and only by modeling them all together can we hope to see the true picture emerge from the digital chaos. The primary goal is to solve the great puzzle of the supernova mechanism itself, to witness in silico how the stalled shockwave is revived. For decades, the models failed, the shock would stall, and the virtual star would simply collapse into a black hole without an explosion. It was only by adding more layers of realistic physics, especially the subtle but immense power of the neutrino wind, that the simulations finally began to work. Now, when researchers run these digital experiments, they can watch on their screens as the neutrino heating reignites the shock, pushing it outward in a triumphant, asymmetric bubble that finally rips the star apart. This is how we bring mathematical order to a physically chaotic process, transforming a flash of light into a structured narrative of cause and effect. Beyond the explosion itself, these virtual laboratories let us track the synthesis of every element. We can follow a single atom of silicon as it is forged in the star's final hours, then watch it get bombarded by neutrons in the Are process during the explosion, transforming it into a heavy element like barium or gold. The simulation can trace the entire journey of that atom as it is blasted outward and incorporated into the expanding supernova remnant. This gives us a complete cosmic inventory, showing not just that these elements are made, but exactly how, when, and where in the cataclysm they are created. The supercomputer becomes a time machine, allowing us to dissect a process that lasts mere seconds, but whose consequences shape the entire galaxy. It is a profound testament to human curiosity that we can take the universe's most violent chaos and contain it within the orderly logic of mathematics, replaying the death of a star again and again until its secrets are finally revealed. This pattern of cosmic abundance is a silent testament to the universe's history of creation. If you were to chart the relative amounts of every element found across the cosmos, you would see a graph that is anything but random. It is a precise and beautiful signature, a chemical fingerprint left by the combined work of every star that has ever lived and died. The line plummets downward from the lightest elements, hydrogen and helium, which are the primordial relics of the Big Bang. Then you see a jagged landscape of peaks and valleys, each telling a different chapter of the stellar story. There is a prominent peak for carbon and oxygen, the ashes of stable stellar fusion. And then, standing out like a mountain, is the iron peak. This is the unmistakable mark of the supernova. Iron is the final element a star can create in its core through peaceful fusion, and its abundance is a direct measure of the countless massive stars that have reached the end of their line and exploded. The elements just beyond iron on the periodic table show a steep drop, a cliff that marks the boundary between normal fusion and the frantic, explosive processes that only occur in stellar deaths. Then you see a curious series of smaller peaks for elements like silver, gold, and uranium. These are the products of the rapid neutron capture process, the Are process, minted in the supernova's chaotic heart or in the collision of neutron stars. This entire graph, from its highest peaks to its deepest valleys, is a macroscopic record of order. It is the cumulative result of nuclear physics operating under the strict rules of gravity and thermodynamics across billions of years. The universe did not start with this complex blend of ingredients. This chemical diversity was built, element by element, in the life and death cycles of stars. Every peak on that chart corresponds to a different method of cosmic forging, a different chapter in the universal recipe that turns simple hydrogen into the rich variety of matter needed for planets, oceans, and life. That chart is not just a collection of data, it is the autobiography of the cosmos, written in the language of atomic nuclei. That chart of cosmic abundance is not just a distant scientific graph, it is the very recipe for your own body. Every single time you take a breath, you are drawing in oxygen atoms that were fused in the core of a massive star billions of years ago. The iron coursing through your veins, binding to oxygen in your red blood cells to keep you alive, was the final, doomed creation of that same star's furnace. The calcium that gives your skeleton its strength was forged in that stellar inferno and then blasted into the galaxy by the supernova's fury. We are not just metaphorically connected to the cosmos, we are literal, walking collections of recycled stardust. Every person you have ever met, every living thing you have ever seen, is composed of atoms that were born in a cataclysm of unimaginable violence and then carefully assembled over billions of years. This knowledge transforms our place in the universe from one of passive observation to one of intimate participation. You carry the legacy of stellar death within you, a permanent, living monument to the universe's incredible power to create order from chaos. The very substance of your being is a testament to the fact that destruction and creation are two sides of the same cosmic coin, and that our existence is the most beautiful and intricate outcome of that eternal process. This steady enrichment unfolds across billions of years, a cosmic timeline written in elemental ink. In the very beginning, the universe was a blank slate, composed almost entirely of hydrogen and helium, the raw remnants of the Big Bang. From this pristine gas, the first stars ignited. These were the population 3 stars, colossal titans of pure primordial fuel. They lived fast, burned hot, and died young in the universe's first supernova. Their violent deaths were a revolution, the first time the cosmos was ever polluted with elements heavier than helium. They seeded the void with the first traces of carbon, oxygen, and iron, a foundational sprinkle of complexity into a simple cosmos. This newly enriched gas then mixed with the remaining primordial hydrogen, and gravity began its work again, pulling this richer material together to form a second generation of stars. These population 2 stars were born with a legacy already written into their composition. They contained a small but vital dash of those first heavy elements. This tiny metallicity made all the difference, allowing dust grains to form more readily in the clouds that birthed them. With dust came the ability to build solid planets. Our own Sun is a proud member of the 3rd generation, a population 1 star. Its substance is the most chemically rich of all, carrying within it the accumulated ashes of countless generations of stellar deaths that occurred long before it was born. This is the grand timeline of cosmic chemistry, a story of steady enrichment where each stellar generation builds upon the work of the last. The universe is not static. It is a dynamic system that grows more complex and diverse over time, transforming itself from a realm of simple gases into a cosmic repository of all the elements we know and are. Yet for all its creative power, the supernova does not work alone. The origin of the heaviest elements, forged in that frantic neutron capture, remains one of the most compelling mysteries in modern astrophysics. For decades, astronomers pointed to core collapse supernova as the primary cosmic forges for elements like gold and uranium. The violent conditions seemed perfect. But as our simulations grew more sophisticated, a problem emerged. Many supernova models struggled to produce the sheer abundance and specific mix of these heavy elements we actually observe in the universe. The explosions were either not robust enough or did not provide the perfect, sustained torrent of neutrons required. The cosmic inventory did not match the crime scene. This discrepancy forced scientists to look for another, even more extreme culprit. The spotlight has now shifted dramatically to the collisions of neutron stars. When these ultra-dense remnants spiral together and merge, they create a maelstrom of unbelievable density, spraying out clouds of neutron-rich material that is perfectly primed for the rapid neutron capture process. The brilliant glow of a single neutron star merger, observed in gravitational waves and light, provided stunning confirmation, revealing signatures of newly forged gold and platinum being created in real time. So which is it? Does gold come from a supernova or from colliding dead stars? The most likely answer is both. The universe, in its infinite creativity, seems to have multiple pathways to complexity. Core collapse supernova probably contribute a portion of these precious elements, while neutron star mergers contribute another, perhaps even larger, share. The precise recipe is what astronomers are working to pin down right now. This is not a sign that our earlier ideas were wrong, but rather that our understanding is deepening. We are witnessing science in motion, a live investigation into the very origins of the matter that makes up our world. The fact that we are still debating where the atoms in our jewelry come from is a thrilling reminder of how much we have yet to learn about the chaotic, creative engines of the cosmos. This stellar alchemy directly shapes the potential for life itself. The chemical richness of a galaxy, what astronomers call its metallicity, is not a minor detail. It is the fundamental prerequisite for building a living world. Think of it as a cosmic pantry, a galaxy with low metallicity, one that has experienced few supernova, is like a kitchen stocked only with salt and flour. You can make some basic things, but you will never bake a complex, layered cake. In such a place, planets that form will be gaseous or barren, lacking the wide variety of heavy elements needed for complex chemistry. Now consider a galaxy like our own Milky Way, which has been steadily enriched by countless stellar explosions over billions of years. Its pantry is overflowing with ingredients: carbon, nitrogen, oxygen, phosphorus, and sulfur. When a new star like our Sun forms in such a rich environment, the planets that coalesce around it are built from this diverse and complex stockpile. They are rocky worlds, rich in minerals and metals, with all the necessary atomic building blocks for molecules like water, amino acids, and the nucleobases of DNA. The very elements that form the backbone of every known biological molecule were forged in supernova. This means the rate of these stellar explosions throughout a galaxy's history is not just a measure of its chemical evolution, it is a direct indicator of its biological potential. A galaxy with a vibrant and ongoing cycle of stellar death and rebirth is actively cultivating the conditions for life. It is transforming primordial simplicity into a cosmic garden of chemical complexity, where the seeds of biology can finally take root. This cosmic truth forces us to reconsider our most basic categories. On Earth, we see creation and destruction as polar opposites, two ends of a spectrum where building something requires careful effort and tearing it down is a moment of loss. But the universe operates on a different, grander logic. Here, the most profound acts of creation are inseparable from moments of ultimate destruction. A supernova is not an exception to this rule. It is the ultimate expression of it. The star must die, its stable structure shattered into chaos for new elements and new worlds to be born. This is not a cycle of death followed by life, but a single, unified process where death is the very mechanism of life. The iron in your blood exists because a star's core collapsed into nothingness. The calcium in your bones exists because a stellar furnace was violently torn apart. The two are not sequential, they are two sides of the same cosmic coin. This challenges the very way we perceive our own existence. We often view stability and order as the ideal states, the goals to strive for. Yet the cosmos reveals that chaos and violence are not aberrations, they are essential tools in the universe's workshop. Without these periodic, catastrophic resets, the universe would remain a sterile, simple place, a vast ocean of hydrogen with no possibility for planets, oceans, or minds to contemplate it all. The supernova teaches us that the path to profound complexity is not one of gentle accumulation, but one of necessary, transformative violence. It suggests that our own lives, with their moments of breakdown and rebuilding, might be mirroring this fundamental cosmic pattern on a human scale. Are our own personal endings also hidden beginnings, woven from the same fabric of destruction and renewal that built the stars themselves? Our cosmic investigation is about to leap forward in an unprecedented way. The next generation of observatories now coming online will transform supernova from rare, fleeting events into a rich statistical data stream, the Vera-C. Rubin Observatory, with its immense camera capable of scanning the entire visible sky every few nights, is poised to discover tens of thousands of these stellar explosions every single year. It will find them in galaxies so distant their light has been traveling for billions of years, giving us a live broadcast of the universe's chemical evolution across cosmic time. We will no longer study individual supernova as isolated curiosities, but as a vast population, revealing patterns we can barely glimpse today. This flood of data will be complemented by the piercing infrared gaze of the James Webb Space Telescope. When a new supernova is spotted, Webb can immediately turn its instruments toward it, dissecting the light from the expanding debris cloud in phenomenal detail. Its infrared sensitivity is the key. It can peer through obscuring dust to see the inner heart of the explosion, and it can detect the specific chemical fingerprints of elements that are invisible to optical telescopes. For the first time, we will get a nearly complete inventory of what each type of supernova produces. We will be able to measure the precise amounts of carbon, oxygen, silicon, and iron blasted into space. We might even catch the direct signature of heavy elements like gold and silver being forged in real time, finally settling the debate over which cosmic events are the true factories for these precious substances. This is not just about counting explosions, it is about reading the detailed recipe book of the universe. Each supernova is a page in that book, and these new telescopes will allow us to read millions of them, tracing how the proportions of each element have changed from the early universe to the present day. We are on the verge of moving from understanding the story of a single star's death to compiling the grand history of cosmic creation itself. A star's chaotic death is therefore the universe's ultimate act of creation. From that single, violent event comes a chain of existence stretching across billions of years. The iron core that doomed the star becomes the iron in our blood, carrying life-giving oxygen through our veins. The silicon forged in its layered heart becomes the very rock of the world beneath our feet. The carbon, nitrogen, and phosphorus scattered by the explosion become the fundamental building blocks of our DNA. This is not a poetic metaphor, but a physical reality. We are the universe becoming conscious of itself, assembled from the ashes of its most powerful explosions. Supernovae are not merely destructive ends. They are essential, creative acts that transform simple hydrogen into the rich complexity required for planets, oceans, and life. They are the cosmic engines of renewal, ensuring that no stellar death is in vain. Every time you look up at the night sky, remember that you are not a separate observer. You are a part of this grand, ongoing story of destruction and rebirth, a living testament to the cosmos's incredible power to build intricate order from profound chaos. If this exploration of our cosmic origins has changed your perspective, we invite you to subscribe for more journeys into the universe's greatest mysteries. We would love to hear your thoughts on this incredible story in the comments.